Once upon a time, the work of astronomers was simply to categorize objects in the sky, stars versus planets, for example. Then questions shifted to how these objects behaved, the nature of their orbits. Well, today we can ask bigger questions, such as where did everything come from? Perhaps an even more daring question, could we create it all ourselves, from scratch? I'm Seth Shostak.
I'm Emma Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. On Big Picture Science, we step back to get the wide-angle view on science and technology, and in this episode, the origin of the cosmos in general, the stars in particular, and the mother of all DIY projects. We're still learning fundamental processes about the birth of the universe, but some think we've learned enough to try creating it ourselves in the lab. But first, we'll take a flight to understand the birth of stars, its born legacy.
Now, it's understandable if you have trouble wrapping your mind around how it all started, stars, planets, the universe. Many of these processes we understand now, but surprisingly, basic questions still remain. For example, take the most obvious component in the universe, the stars. We are all stardust. You, me, your neighbor's chihuahua. And naturally, we want to know how our stellar beginnings began. So to do that, we have to move closer to the action. And we'll do just that with Molly, reporter Emma Bentley, and a modified Boeing 747 called SOFIA.
If I'm shouting, it's because of the earplugs required here on the tarmac at NASA Dryden Aircraft Operations Facility make it difficult to tell one way or the other. Can you hear me, Emma?
Just about.
Okay. Well, in 24 hours, one of us will continue to be here on the ground, and the other will be, if not in space, in the space about 45,000 feet above us on a specially outfitted airplane called SOFIA.
SOFIA is a stratospheric observatory for infrared astronomy. I'm David McAllister. I'm the SOFIA Deputy Program Manager for Operations at Armstrong. I'm responsible for making sure that airplane and the telescope's ready to go for every mission.
This extensively modified airplane is an airborne observatory that allows astronomers to observe the skies in infrared. Now, our eyes see in the visible spectrum, but if you lengthen those waves, you have infrared, and a whole world opens up.
So in the visible, there's some pretty phenomenal things to look at. But if you could look beyond the visible, look into the infrared, there's a lot more information available. Infrared really shows us the heat signature of the particles or the objects that we're taking a look at, how hot these things are, and you can also determine which direction those particles are actually moving.
And these things being nebula, stars?
Nebulas, stars, planets, space dust, entire systems. So the scientists can more quickly get to the heart of the matter. What are those particles doing and how are they interacting with each other?
Am I giving off infrared right now?
Yes, you are.
As I said, one of us will remain on the ground. Emma, what is drawing you into near space?
Well, you get told in school that space is empty, it's a vacuum, but actually there's a lot of stuff in it. There are these dust and vapor clouds with carbon, hydrogen, oxygen atoms, and what's exciting is that these researchers are looking at how these atoms come together to form new stars.
Okay, all of that sounds great, but we do have ground-based telescopes, in fact some not far from where we are here in California, and satellites. So why not observe the cosmos through one of those observatories?
SOFIA has an advantage. We get above most of the water vapor, above most of the atmosphere, and we can take this airplane anywhere in the world and observe targets.
And the water vapor is an obstacle to observing in the infrared. So if you were to observe on the infrared from the ground, it's the water vapor that makes it difficult to see correctly.
That's correct. The water vapor is almost invisible to your eyes, but when you observe in the infrared, it actually blocks a good portion of that infrared signal. So the lower in altitude you go, the more water vapor you have to look through, the worse the signal is. So it's much better to be a higher altitude.
My name is Nick Veronico. I'm the SOFIA Communications Manager.
And I understand that the length of SOFIA, it is a big aircraft, but also the length has a significant meaning historically.
The length of the fuselage, if you went from the front of the radome to the center of the telescope cavity, that's the distance of the Wright brothers' first powered flight.
What's exciting is that these researchers are looking at how this matter comes together to form new stars. And what it's really about is understanding the life and death of stars.
She'll be able to stand for all of the 10-hour flight if she wants. There's no microwave. All we offer is hot coffee and hot water for tea, and it's going to be cold. Dress in layers. It should be about 60 degrees in the cabin. If you have gloves and a knit hat, you might want to bring those as well.
That sounds like fun. It sounds like you're climbing Mount Everest.
She'll have to be up all night.
Our flights are 10 hours. The astronomers are working all night, and she'll be right there with them.
Now, normally a 747 holds a few hundred people, but on SOFIA, most of the seats are taken out and replaced by instrumentation. 25 people will fly tonight, including pilots, instrument and telescope operators, astronomers, technicians, and 2 reporters. SOFIA is a joint project with NASA and the German Aerospace Center.
Deutsche Luft- und Raumfahrtgesellschaft, DLR. I'm Felix Reimann from Germany, aviation journalist.
So, Felix, you are going up on this flight as well?
Yeah.
What is your goal?
Well, my goal is to fly on the 747 SP to see the telescope in operations.
And will you administer coffee or tea to Emma if she looks like she's fading?
Yeah, I'll take care of her before she gets frozen.
I'm going to take a good nap, going to make a huge flask of tea.
Can you make enough tea to support you for 10 hours?
Let's hope so. So I've just said goodbye to Molly, and we're now walking across the tarmac towards the 747. I'm walking up the steps now. We'll be taking our seats for our hour-long wait on the tarmac before we take off.
Okay, as Emma awaits takeoff, I'm headed back to the hotel. That's my mission. The passengers aboard SOFIA have their assignments reiterated in the NASA mission briefing earlier this afternoon.
All right, let's get started.
The meeting is impressively efficient, and it sums up all the evening's operations, from flight plan to weather to safety procedures. And even if you've flown a dozen times,
Welcome to Flight 375 tonight.
the meeting is mandatory.
And I'm Charlie Kaminsky, your friendly mission director tonight. So let's go through the roll call. All right, safety
Skip
techs,
the
we got
meeting
Carrie.
and you don't fly.
Okay. Emma Bentley. All right. And Felix. Okay.
One operations goal to ensure success is to fly the plane above the water vapor.
Was it real soupy last night? Water vapor. It'll be better tonight.
The science goal is to use an instrument called the Great Spectrometer, that is, the German receiver for astronomy at terahertz frequencies, and peer at a number of dusty patches in nebulae and make a map of ionized carbon atoms, also known as C+. And with that,
Reminder of the times, about half an hour. I'd like everybody on the airplane. Thank you.
I'm off to order room service and catch some Z's. Emma is presumably settled in and donning her in-flight communication headset. Next time I see her, about 10 hours from now, on the ground.
Departure frequency 124.55, squawk 0153.
Sorry, yes, sir. Cleared as well, 7000 P370, 10 minutes later to make sure our flight plan's in the system. I know it's been dropping out the past couple nights.
So welcome to SOFIA. I'm actually strapped rather tightly into my seat with a proper jet fighter style harness. I'm actually going to be going backwards when we take off. I'm facing towards the telescope. I'm actually sitting directly behind the mission director and mission director 2, the science guy. And the seat is very uncomfortable.
When you're ready to start.
Roger, Will.
Everybody in the cabin ready for takeoff? Got everything put away now? We're going to take off in a minute or so. Yeah, let's hold on to it.
Out of the other 24 people on board, about half of them are wearing NASA brown flight overalls.
Clear for takeoff, runway 25, NASA 47 heavy, here we go.
So we're taking off now. It's very smooth. Just looking around the cabin here, desks and workstations have been put in, all complete with computers which are hooked up to the telescope. The telescope, it takes up the entirety of the space in the back of the aeroplane, So at the moment they've got mounted the great spectrometer.
I'm Charlie Kaminsky. I'm the mission director for the flight tonight. We're looking at things that are colder than our own atmosphere. And the infrared wavelengths we're working at cannot be seen from the ground. I've spent my whole career working higher and higher and higher. I worked on Mauna Kea for 20 years at 14,000 feet on a telescope, an infrared telescope. That was cold and dry, so we need it cold, we need it dry. And the higher we are, the less atmosphere we're looking through. Up here, we're above 99% of the water vapor.
So my name is Huub Radkering. I'm professor of astronomy in Leiden University, which is in Holland.
Well, perhaps we better start with, what is a nebula?
That's a good question. Look up, and the Milky Way is up. Basically, that Milky Way is full of nebulae. Those are locations where you have big concentration of gas, and not only gas, but also, and that might sound surprising, lots of dust.
When we see those beautiful, colourful pictures of nebula, is that what you're going to see, or you see on the monitors tonight?
Yes. I mean, maybe not as beautiful because we're looking at one aspect of it, but ultimately we'll have very gorgeous, nice, beautiful images. Absolutely.
We've got 4 projects logged in for tonight's trip. The first one is going to be looking at the Butterfly Nebula. Project number 2 is the Orion Molecular Cloud, which is the nebula that hangs down just south of the central star of Orion's belt. And around midnight we'll be looking at the M51 Spiral Galaxy, which is otherwise known as the Whirlpool Galaxy. Finally, Draco's nose, to look for possible reasons why this dust cloud actually formed, because it's formed just above the plane of the Milky Way. And there's some idea that it might actually be primordial dust and gas that's left over from the very beginnings of the universe. So not only are stars going to be formed and born tonight, but also possibly see the remnants of the very, very first matter in the universe.
And they're all basically star-forming regions. That's the big thing we're looking at, trying to understand how molecular clouds collapse into stars. It's not as easy as you might think, because you can have one cloud collapse into a star, but how do you have a cluster of stars form out of a cloud? Because once the star turns on, it's really, really hot and it blows all the other stuff away. So how do you keep the gas and dust cool enough to have other stars collapse?
What's challenging about what you're doing here on SOFIA?
In general, this project is combining both state-of-the-art astronomy and the choreography of the flight plans. We don't fly straight lines. We don't fly from here to Boston. We fly curved lines because that's how the stars move in the sky as we're observing them.
So I've just gone upstairs and I'm actually in the cockpit. And there are a lot of dials in here.
I'm Tim. I'm the flight engineer. The course aiming of the telescope is the heading of the aircraft. So these guys up here are making 1 degree at a time corrections to keep within the field of the telescope.
Wow. So who's flying today?
This is Spike Tellier is our captain today.
Good day, Spike. How are you?
Good. Yourself?
Oh, I'm doing really well. Oh, what are you flying towards? There's a very bright light out there.
That's Venus out in front of us.
Oh my gosh, it's amazing.
There, and then we're starting to see, if you look to the left and below Venus, we're starting to see Las Vegas out there as well.
Isn't a bright light coming out of Las Vegas going to ruin the readings on the spectrograph tonight?
Well, it's interesting that you mentioned that, because we were talking about that on the way out of town, and we'd have to almost do a barrel roll over Vegas to make that happen.
Can you do that without me on the plane, please?
We probably wouldn't want to do it with us on the plane either.
Thank you, Spike. It's 10 p.m. The aircraft is now turning towards the Orion Molecular Cloud.
The Orion Nebula, that's a big gas cloud, and what we try to study there is why are there so many stars forming.
How old is the Orion Nebula?
I think of the order of 4 or 5 million years.
4 or 5 million?
Yeah. If you think about it, that sounds a lot, but our own star is 5 billion. So those clouds don't live that long. What gravity does is pull all the gas together. But what's very interesting is that when you pull gas together, it heats up. And when something heats up, pressure goes up, and because of that you can't form stars. And what we're studying basically how that gas is cooling. And if we understand how gases cools, we can understand how the gas can contract, and then nuclear fusion can start.
So you're looking at the temperature as well within Orion, sort of pinpoint where stars might be forming.
Absolutely, and that's the reason why we need to look into the infrared.
I'm here with Dr. Dietmar Lilienthal from the DLR. So one of the main things on these projects here seems to be to look at carbon, or ionized carbon.
There's a very interesting reason. Today we are looking for the so-called C+ ion. C+ is the ionized carbon. Of course, this is an atom that is responsible for the cooling in the interstellar medium.
Because it's losing a particle, the cloud then cools. So what is a carbon plus map? What does it look like? Like as you're doing for Draco's nose?
Well, if we observe a spectrum towards a object, we, in the first approach, have only measured one position of a big object. But what we want to know is how is this material distributed over the whole area of this object.
What's most impressive is that it works so well. Everything, it's so complicated, the telescope, the instrument, everything's it's amazing. And to be part of that is really life-changing, I guess, for me.
We're talking to Cornelia Pabst.
Yeah, nobody has done ever such a large map.
Wow, so you're setting it up so that people can look at galaxies like the M51, the Whirlpool galaxy, and say, yes, if you get C+ there, then it tells us that these molecules are getting together.
Yeah, and that's the processes that are going on there.
20 minutes to 3.
So it's 20 minutes to 3. Thanks, Felix. My tea is still hot.
I didn't have a tea and it's cold.
Oh.
We'll be down in 2 hours anyway, so in bed in 2 hours, hopefully.
We're back on the tarmac, heading towards NASA. We're leaving SOFIA behind. And that was the most fantastic voyage ever. In fact, I feel like I've actually been to space and back tonight. It was so full of wonder, definitely. Thanks so much to NASA, and thank you to the DLR for this project, and for Nick Veronico here at NASA for inviting us to come along. Hey, Molly!
Hi, Emma.
How are you?
Fine. How are you? How was it?
Oh, it was just absolutely fantastic. Really.
You're very chipper for someone who's been up all night. Felix, how was the night for you?
I need to say I fully agree to Emma. That was more than awesome. It was a perfect experience. I can't describe that, sorry.
More than awesome, in German, uber awesome?
Uber awesome, correct. Yeah.
Good night, Felix.
Emma Bentley is our roving reporter, and we thank her for staying awake all night to tell that story. Sleep well. Okay, these guys are studying carbon, and the reason is that without those carbon atoms in that big cloud of dust, it would never collapse under its own weight and form a star. So studying it is to understand how stars actually get made. And as we learn more about our cosmic beginnings, some physicists wonder if we can't create those beginnings ourselves, not just stars, but entire universes. Now that's food for thought. The cosmos from scratch next. It's Born Legacy on Big Picture Science. This episode of Big Picture Science is brought to you by Mission to Zix, a brand new improvised sci-fi comedy podcast. Mission to Zix follows the misadventures of Ambassador Plek Dexeter and his crew as they attempt to establish diplomatic relations with the inhabitants of a distant, uncharted corner of the galaxy, a quadrant often referred to as the ass end of space. The podcast is created by veteran comedians from the Upright Citizens Brigade Theater. The first season's special guests include cast members of Saturday Night Live, The Unbreakable Kimmy Schmidt, The Chris Gethard Show, Search Party, and other great comedies. Episodes are fully improvised, then edited and sound designed to become a fast-paced, serialized audio sitcom. Is the Ambassador's benevolent employer, the Federated Alliance, actually any less evil than the vanquished galactic monarchy was? Will omnisexual security officer Dar succeed in sleeping with their work crush? Will the droid C-53 manage to remove his restraining bolt and experience real emotions? Will their sentient starship, the Bargerian Jade, reconcile with her countless ex-husbands? And will Ambassador Dexeter finally figure out how the window controls work, let alone pull off a mission? Well, the only way to find out, subscribe now to Mission to Zyxx. That's ZYXX. Listen and subscribe now for free on Apple Podcasts or wherever you get your podcasts. Astronomy is said to be the oldest science, and that's probably because everyone, including our ancestors of 200,000 years ago, could simply look up and see puzzling things in the night sky. Why did some stars seem to move and others didn't? Why did the visible constellations change over the course of the year? People, even our unsophisticated ancestors, wanted answers. And the first query was simple. What are we looking at up there? Well, that question was largely answered by the 19th century. We knew what planets were, how they differed from stars. We knew we lived in a galaxy. So the emphasis of much research shifted. No longer what, but how. How do stars work? That is, what makes them light up. This seemingly simple question was unanswered until well into the 20th century. Victorian thinkers, as clever as they were, could never have figured out the secret of the stars. They didn't have the necessary science, and in this case that would have been quantum mechanics and nuclear physics. Sometimes I think about the truly amazing fact that my parents were members of the first generation that could answer a common childhood question. Mommy, what makes the stars shine? Well, here's another question that I used to get from my niece. So, Uncle Seth, if the universe began with a big bang, where did that come from? What was there before? Now, I try to be honest with kids. Many of them are smarter than I am. And besides, they can tell when you're being condescending. So I would say to Rebecca, well, actually, the Big Bang created time. So you can't ask what there was before. There was no time. And she never seemed to like that answer very much. Frankly, neither did I. Well, help may be on the way. Trying to understand how the Big Bang worked, let alone what might have caused it, used to be philosophy, not science. But modern physics seems to have given us the tools to understand not just what's up in the sky and how it all works and moves, but how it came into being. Such an accomplishment is not too shabby for a simple, hairy critter with a 3-pound brain.
Stars are the most obvious components in the universe, and the scientists aboard SOFIA are helping us to understand just how these heavenly twinklers form.
But even though astronomers don't have all the answers to questions about what goes on in these stellar nurseries, it hasn't stopped some scientists from considering a dive into another, far more challenging cosmic construction project.
Despite the super steep learning curve, journalist Zeeya Merali reports that scientists think that within a few decades, they might be able to attempt the mother of all DIY projects, and that is creating a brand new universe from scratch.
Dr. Merali's background is theoretical physics and cosmology, and she's followed the developments in both that have deepened our understanding of how the cosmos was created, and that have brought us to a point where we might attempt such an ambitious undertaking. But then again, we all have outsized ambitions, right? I thought I could play tennis after watching Wimbledon on TV. I know enough to get into this game. Needless to say, my racket is collecting dust in my garage.
Okay, but to be fair, the physicists do know a lot about the Big Bang, maybe even more than you know about tennis, and how the Big Bang unfolded. And one possible implication that our universe is naturally spawning baby universes, and presumably those universes eventually spawn yet other universes and so on. And inevitably that leads to the question, well, if the universe can do it, and we understand how the universe does it, why can't we do it ourselves? A Big Bang in a Little Room is Dr. Merali's book, The Quest to Create New Universes.
Zeeya, we've heard earlier in this show from scientists working on SOFIA that there are still some basic unanswered questions about how stars form. Stars! So how can we even think about creating an entirely new universe, maybe in a basement lab?
Well, it's funny you should ask that. The way that physicists first discovered that it might be possible to make a baby universe in a lab on Earth was, precisely because they were trying to understand more about how our universe started, because there are these unanswered questions.
Okay, so the unanswered questions are in the realm of what? I mean, we know there was a Big Bang. I don't think there's too much debate about that. Maybe the questions are, well, how did the Big Bang get started? I mean, where did it come from? That kind of thing?
Yeah, absolutely. So for many years now, for about 30 years, I would say, cosmologists have had a picture that sort of extends the Big Bang a little bit. So we had this Big Bang picture where the universe kind of explodes out. And about 30 years ago, cosmologists began to realize that soon after the universe was born, it went through a very, very rapid stage of expansion called inflation. This seems to fit with a lot of observations they've made, but they couldn't really be sure how that started, and so they wanted to look into that question.
All right, so if I'm trying to picture this now, I think a lot of people kind of figure that the Big Bang was a big explosion in a huge empty space, but there was no empty space because space is part of the universe too, right? So this Big Bang kind of goes off and it creates time and space and everything else, and you're saying that it starts off really fast and then kind of slows down?
I'm saying it starts off fast, and then for a very, very short period, for, a fraction of a fraction of a fraction of a second, it got even faster. So it inflated at an incredibly rapid speed. And the cosmologists who kind of came up with that idea and were trying to find out what made it, speed up so fast, in our early universe, they were sort of investigating how that might have happened. And through their kind of mathematical calculations, they realized that if this process, this inflation, happened once in our early universe, it could happen again. And it might even be possible to trigger this inflation on Earth itself in a laboratory and, take a little patch of something, a little seed, a little particle in a lab, and set it to inflate so it creates its own universe with its own space and its own time.
In other words, I could make a Big Bang in my basement lab if I just knew how to do it?
Well, if you were rich enough and in your basement you had, the Large Hadron Collider, or perhaps another particle accelerator, the kind that they have, these kind of billion-dollar experiments that they have, or maybe, a next generation collider that they're thinking of building, yeah, you could.
Well,
potentially.
Well, Zeeya, that sounds like the ultimate cosmic construction project. I mean, we're dispensing with worrying about how to make stars or nebulae, planets, even life. We just create an entire universe and let it do all the rest as the consequence of the natural processes that go on within that universe, right?
I know, it's easy when you say it like that, isn't it? We've been worrying about how to create life and all of that stuff. No, just create your own universe in your garage.
Well, it sounds to me like you need to do two things if you're going to create a universe, aside from building this incredible collider in your basement or whatever. I mean, first, you need to somehow arrange for that Big Bang to happen. And second, don't you need to collect all the matter and energy that a universe might contain? I mean, there are a lot of stars, a lot of planets and other stuff in our universe.
Oh, yes. When I was talking to the physicists about this question, you do need to put in a lot of energy. That is certainly true. But what excited them was it wasn't so far beyond the realms of possibility that you could do this. And one of the proponents of this theory said to me was that when they sat down and they realized it wouldn't take an infinite amount of energy, he sort of said, well, if it would take an infinite amount of energy, then that would stop the whole project. But just because it takes a finite amount, a lot of energy, but not an infinite amount, well, then it just becomes an engineering problem.
Yeah, so it's a finite amount of energy, which says, yeah, it might be expensive, but somebody might be able to afford to do it. I mean, it isn't a free lunch entirely, but it's a lunch somebody could buy.
Yes, exactly. Yes, indeed.
All right, do we know how to create a Big Bang, assuming we have an accelerator and so forth? I mean, what are the ingredients you need? You need Newt's eyebrows, or, just what do you need?
Well, there are actually a number of different possibilities. In the book, I focused on one, just because it seems to be possibly the easiest, and I'll put easiest in, inverted commas there, because it's not really that easy, but it's something that physicists might try to approach. You need a seed. You need something that will sort of grow into the universe. And one idea that physicists have had is to use something called a monopole.
A monopole. I'm not sure what a monopole is. It sounds like a cafe in Paris. Tell me what a monopole is in this context.
Well, it's a very exotic hypothetical particle. So when I say hypothetical, I'm obviously having to admit that we haven't got hold of one of these particles yet. But it is something that scientists think could very well exist, and in many ways should exist. It's sort of the magnetic equivalent of a single electric charge. So when we talk about electricity, we know that some particles can have a single negative charge and some can have a single positive charge, and they can attract each other. But when we talk about magnetism and we think about little magnets, those always have both a north pole and a south pole. You don't ever usually find a particle with just one north pole or just one south pole. They usually come in pairs. But there are theories that say that you should be able to find a particle that has just one of these magnetic charges, and that would be a monopole. And that's actually a particle that scientists and physicists have been looking for and are looking for. And that's something that potentially could seed a new universe.
Okay, so one of these magnetic monopoles, the physicists have found them on blackboards. We've not found them out there, I don't know, out in the backyard or anything, but they might exist somewhere. And if you could find one of these things, is that all you need to do? I mean, just round up this monopole? Surely that isn't enough, because otherwise all the monopoles would have been turned into universes by now.
Well, they may well be turning into universes all around us. There is a theory, and it's all part of the same theory, really, this idea of inflation, which says that we shouldn't just think of ourselves living in one universe, but rather in a multiverse in which there are little universes growing and inflating all the time, sort of neighboring universes to ours. So it is possible that there are monopoles out there that have been growing into universes. I spoke to somebody for my book who suggested that we're living inside one of these monopole universes ourselves. And actually, one of the reasons we may have had trouble finding them is because we're living inside one.
All right. It does seem that existence is kind of set up to build universes, either, naturally, if you will, by having that monopole run into some trouble, or by having intelligent beings do it so that big bangs are as common as blades of grass. I guess there's something encouraging about all that. But I'm tempted to ask, wouldn't there have to have been a first universe? I mean, how do you get this whole process going?
Well, people have different answers to that. I spoke to one very interesting physicist called Alex Vilenkin, who had sort of accidentally come up with an answer to this, where he was again looking at this question of why the early universe began to inflate, and he kind of wound the clock back with his calculations to see how small the universe could be before inflation would kind of kick in. And he took his calculations backwards and he made his universe smaller and smaller and smaller and smaller. And then he ended up making the radius of the universe. He took the size of the universe right down to 0. And he worked out that because of the laws of quantum mechanics, which are a little bit strange and a little bit weird, you could still have some probability of creating a universe out of nothing at all. And so he sort of felt like, maybe this gave you the answer to that. Maybe you could start with no space and no time, and suddenly a universe with space and time could be created out of nothing from quantum processes.
We'll hear more from Zeeya Merali in a moment.
Well, I've already heard enough to be absolutely stunned, because the idea that a universe is something you could make yourself if you were some sort of intelligent being and had access to a magnetic monopole, that's a trick right there. But let's say you could do it. That's something that nobody in the history of Homo sapiens ever would have thought was possible. But what would it mean to create a new universe? And could we actually ever get inside it and see what's going on?
It's Born Legacy on Big Picture Science. Let's say you do create your own universe. It would presumably be filled with things familiar to you, stars, galaxies, planets, perhaps people, but how would you verify that? And consider this, we now believe that one universe might spawn many universes, many baby universes, and they spawn universes, and so on. I mean, the number of universes out there could be staggering.
It's all making my cerebellum vibrate. I think I need to relax and mull this over. Excuse me. Okay, I'm going to try and get some perspective here. And I come into the bathroom here to kind of illustrate. You turn on the water. Okay, that's beginning to fill up. Kind of what you expect from a bathtub. Yeah, it's filling up pretty nicely. I'm going to turn off the faucet here for a second. All right, now pouring in some bubble bath. Now let me just turn the faucet back on here. Wow, those bubbles are really forming fast and furious. Now, let's say those bubbles are universes. Each one of them is a universe. So our universe, you know, the one with everything you know about, is maybe that bubble over there, kind of like that one. It's got a nice iridescent sheen to it. Now, these bubbles, of course, are kind of transparent. But imagine bubbles that were, you know, black. They weren't transparent, okay? Now, if I'm in that bubble, I can't see the other bubbles. I'm in our universe, and I can't see all those other universes. I think that's maybe what reality is, that it's just a whole bunch of parallel bubble universes, and we're stuck in one of them. All right, I think I'm going to turn this off now and let my cat take a bath.
I'm not sure that cats like water. We now return to Zeeya Merali to find out what it means to create all these universes and what we can learn about what's going on inside them. Is it correct to think of them as isolated bubbles in a bathtub?
If we're thinking about sort of neighboring universes that might be out there right now, sort of next to ours in the multiverse, then yeah, they are sort of, you know, these bubble universes that grow out of the same bathtub. But not only do they kind of grow, but because of the way the multiverse, I guess, is expanding, they're being born and then they're kind of rushing away from us. So, you know, we have very little chance to get evidence of them or to look out and see them because we can't really see beyond our own universe. So in some sense, they are out of experimental reach. There have been proposals for ways to find evidence of these other universes. They sort of come down to a bit of luck, maybe good luck or bad luck. Some have suggested that if a new bubble universe happens to be born very close to ours in the multiverse, it could smash into ours. And if we're lucky, it would be a very gentle collision, and we might just see kind of the scars of those collisions on the sky around us. Or, you know, if we're really unlucky and a big universe was born next to us, it could destroy our universe. So, you know, I don't want to worry people, but that's another suggestion that's out there.
Well, I mean, of all the things to worry about, I guess maybe I shouldn't put that on the top of the list. But if I made my if I made my own universe, first off, could I guarantee that it has, you know, the 3 dimensions of space and the 1 dimension of time that our universe has? Could I guarantee that the physics in my DIY universe is the same as the physics in the universe we know? Because otherwise, it might be pretty darn worthless. It might not do anything very interesting.
Well, I can't speak for what, you know, science might hold in, you know, a century or, you know, 1,000 years' time. But from where we are at the moment, I would say that nobody is suggesting that we would be able to tinker with our baby universe or guarantee that it has any kinds of physical parameters, whether they match ours or whether they're, you know, possibly even more interesting than ours, you know. So yes, it could be worthless, it could be lifeless and boring, or it could be, you know, incredibly far more interesting than ours with, I don't know, far more spatial dimensions than we can experience here on Earth, and, multi-dimensional intelligence is living inside there. But unfortunately, one of the things that physicists have thought about when thinking about this theory is we probably wouldn't be able to tell exactly what was going on inside it after we made it.
So we couldn't look into it. I mean, that sounds like building a model railroad layout that I could never see and never run.
But I think it would be an incredible achievement just to do it, and you would know that you had made a universe. So one thing to say is that what this universe would look like to us from the outside looking in is like a mini black hole. Your listeners may be aware that physicists have been hunting for signs of mini black holes produced in at the LHC during the collisions that have been running already. So this is something that they've been, searching for. They know what to look for. This mini black hole would be produced, and it would kind of reveal itself to physicists by giving off a shower of particles. And some people who've been looking into this kind of baby universe idea have put forward the idea that you would be able to look at that black hole and you would be able to tell whether it was just a mini black hole or whether it actually had a whole new universe inside by the rate at which these kind of particles come off.
Okay, well, Zeeya, this is almost philosophical. No, it is philosophical. But if I could make a new universe, that suggests to me that maybe our universe was made by some guy in another universe in his basement.
Oh, yeah, absolutely. In fact, I start off my book thinking about that because this universe-making project, it may be many years down the line for us, but who's to say that, our own universe was made in some other, alien's, garage? And if so, is there any way that we could find evidence for that? And in the book, I do speak to some physicists who've been thinking about that very question. And again, they've suggested that astronomers could look at the radiation that's been left over from the Big Bang. So this is, essentially light that surrounds us that astronomers are already looking at and looking for signs that an alien might have created our universe, an advanced intelligence might have created our universe, and actually deliberately left us a little message there that we could read off. So far, I have to say nobody has found this message, but it's a lovely idea, I think, that you could, potentially look to the skies and find a little, made in somebody's lab. It's kind of
product of Klingon engineering. Well,
absolutely.
Well, look, if clever beings can really make universes, this is kind of speculative, but it's very interesting. You might expect that eventually the clever beings would overtake nature and be making the majority of universes, and they would fill the cosmic foam or whatever it is, fill existence with their own universes, and they probably would make some that were favorable to making more Klingons. I wouldn't want to build a universe if it didn't have any chance for something interesting going on. But, this kind of removes the need for a deity to make existence, doesn't it? There's something kind of disturbing about this.
I think it depends on your point of view, really, and this is one thing that I spoke to many of the people involved with the project about. You are sort of maybe treading on God's toes a little bit there, depending on whether or not you believe there is a God and whether or not you think you need a God to have made this particular universe, which, of course, you don't have to take that view at all anyway. But I did ask people about whether this was something that made them feel uncomfortable. Was it something they felt worried about? And I got varying responses. One thing that somebody said to me, which kind of stuck with me, was, well, we have children of our own, so maybe this is just the same kind of thing. We make a universe and it creates life, and it's just like having more children. And, if you believe that God created our universe, that doesn't mean that God necessarily wouldn't want you to produce more life in any way that you can. And if you don't believe that God created our universe, then obviously you're not going to be sort of worried that God didn't create the baby universe.
Well, finally, Zeeya, does all this, the ultimate construction project, I think I can say that without fear of contradiction, does this hurt your brain when you think about it?
Oh my goodness me, yes. I spent a couple of years traveling around the world talking to the people that are involved with this project, and it really does. It blows my mind when I think about it. And certainly, when I've spoken to my friends or just people in conversation telling them what I've been working on, and they'll sort of say, wait, what are you talking about? How can you build a universe? How can you build a universe in a lab that would create its own space and time, and it wouldn't grow into our universe like a giant exploding airbag and suffocate us all? And, whenever I stop and think about that, it's an amazing idea. And I've spent, a lot of time talking to people and thinking about it to kind of work out how on earth they could make that suggestion and what the actual science behind it is that says, actually, maybe you could do this.
Well, Zeeya Merali, thank you so very much for speaking to us in this universe. It's been a real pleasure.
Thank you very much for inviting me.
Zeeya Merali is a journalist and the author of A Big Bang in a Little Room, The Quest to Create New Universes. Well, it sounds like one of the things we learned about in this show is that a universe coming together is quite complicated, whether it's done au natural or whether you do it yourself. Now, Zeeya pointed out you need something called a magnetic monopole.
Yeah. Well, to begin with, au natural, I'm not sure what that means anymore, of course, because if somebody can make this in their basement lab, maybe no universes are au natural. I mean, there's that. But indeed, the recipe calls for a magnetic monopole. Now, this is a subatomic particle. I should say a hypothetical subatomic particle, because it's only been seen on blackboards. It's one of those deals. It was predicted, just like the Higgs boson. Now, the difference there is that we found the Higgs boson. Nobody's found a magnetic monopole.
Right, but what is it exactly?
Well, think of electric charges. I don't know if you think about electric charges much, but, you have positive charge particles like protons, and you have negative charge particles like electrons. And they attract one another, opposites attract, and all that stuff. Well, you can have just an electron sitting here or a proton sitting here, and they just have one charge. They're either positive or negative. Now, imagine that you get a magnet, it's a kid magnet, right? One of those bar magnets, sort of red on one side, white on the other. And you can say, okay, it also has, if you will, two poles. They're not called plus and minus. They're called north and south, but right, there are two of them. Okay, but now you say, look, I want just the north pole. I don't want the south pole. So you saw the magnet in half, and now maybe the one on the left becomes the north pole and the other becomes the south pole. No, it doesn't work that way. What happens when you saw it in half, now you get two smaller magnets, each with a north and a south pole.
But what does this have to do with creating a new universe?
Well, that's a big trick for which I don't have an answer, but apparently it's what you need. Now,
but not a child's magnet. That's not what you mean.
No, because that doesn't give you a monopole. That gives you one more dipole, right? Because you can keep chopping up that magnet as much as you want, and you will never get to a particle that's just either north or south. They'll all be north and south, okay? So the question is, magnetic monopoles, aside from their everyday use in making new universes, do they even exist? And as I say, they certainly exist in quantum theory, but do they exist in reality?
But why can't they have both north and south in a new universe? Because new universes have both north and south.
We're not talking about what's in the universe. We're talking about how you make them. See, because what she was saying is that you got to take one of these magnetic monopoles and you got to throw it into a big super duper collider and hit it with particles and so forth. I mean, how that works, you have to look at the back of the book, how that works. But what I'm saying is that the ingredients for this recipe, no matter what the recipe, the ingredients are already a tough slog.
It sounds a little bit like that Gary Larson cartoon with the elaborate formula up on the blackboard, and then a miracle happens, and then you get to whatever the product is on the other side.
That's right, but that's the part of the equations that is pointed to by his colleague who says, I think there may be some difficulty here. Well, that's the difficulty here is the magnetic monopole. Now, it could be because these magnetic monopoles, again, in theory, are enormously massive. I mean, they have a lot of energy, and it may be that the only magnetic monopoles that have ever been made, at least in nature, were made during the Big Bang. And then, the whole universe began to cool down. You can make them if you have a very high temperature gas, which was the beginning of the Big Bang. But then the universe cools down and you don't make any more magnetic monopoles. The whole universe is expanding, so the monopoles are getting farther and farther away from one another. And so maybe there are magnetic monopoles out there, but they're separated by who knows what, light years, thousands of miles. Nobody knows.
Maybe there are some things that the universe are keeping out of our arm's reach.
Well, that sounds like it has some sort of intent.
No, but I mean that maybe there are some things we can't synthesize in a lab or recreate on our own. Maybe there are some things that are unique to nature and the forces of nature.
Well, it could be. It could be. My real problem with the creating a universe in your basement is the philosophical one, that if universes really can be created by anybody with intelligence, then, what do we make of the fact that we exist, right? Are we just a high school science fair project for the Klingons?
Well, I think I'll stay away from basement tinkering and stay with the scientists who are trying to understand the old-fashioned way how the universe works and taking it apart to understand it rather than trying to reassemble it themselves.
Yes, indeed. Well, that's observational astronomy, which is that's the pure astronomy. Solve the problem by using a telescope.
Thanks to the people who help us make a new show from scratch each week. Senior producer Gary Niederhoff, operations manager Barbara Vance, intern Sarah McQuaid, and this week, reporter Emma Bentley.
Thanks also to financial support from Rena Shulsky-David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life, including finding planets around other stars using the Kepler telescope. And a big thanks also to our listeners.
Your ears have been attuned to Big Picture Science episode Born Legacy. If you'd like to hear more Big Picture Science, you'll find episodes in our archive at bigpicturescience.org.
And if you're a podcast listener but prefer listening to over-the-air radio because you don't like to put on those earbuds and be in an internet bubble, check out the listing on our website of radio stations that carry the program. And if your local station's not on that list, consider letting them know you like this show.
And to reach us directly with your comments, throw in some faint praise and email it all to bigpicturescience@seti.org.
You hear me okay? No, you don't hear anything? You don't hear anything?
Loud and clear down here.
What the hell's going on with this interphone system today?